Thank you, Jimmy. Hi, I'm Rafi. I'm a PhD candidate from Wayne State University. So today we're going to talk about our paper in this year's CVPR, which is called WalkGPT Grounded Vision Language Conversation with Depth Hour Segmentation for Pedestrian Navigation. So that being said, what we are doing in this paper is we're targeting the pedestrian navigation itself. So before going into further details, I would like to clarify like what is pedestrian navigation. Let's say for our case, if a person gives a first-person view image to a machine learning model or something, the model provides a complete assessment of the path ahead and also provide information like okay, which part is safe to work and which part is to avoid, how far are they are, how far the obstacles are, all these kinds of things. And for this kind of pedestrian navigation, there are like some of the things that user must know, like especially for somebody who has some, like especially for somebody who is challenged and like has low vision or vision impairment issues. So let's say a person who's walking on a path and it gives an image to a machine learning model. The best model would a good model should tell the person himself or herself like what are the walkable surfaces are, like what kind of hazard in the image there are. Also, kind of like a geometric understanding, like let's say for segmentation mask, like say there's a tree and like what the tree shape is and how do you want to get away evade the tree itself. And let's say distance estimation, like there's a tree and how far the tree is. So those kind of all information is in the pedestrian navigation that we are talking about. Um, and why it matters, since it's like, as I was saying, like especially for persons with has mobility challenges, which is for whom the navigation is especially critical, and they face diverse mobility challenge for people and also for like a general walkable assistance. So this kind of pedestrian navigation can be a very important task in the daily life. And this kind of navigation stuff is like mostly focused on like vehicle, like smart vehicles, like Google Map and all like automated vehicle stuff. So this area of focus, it kind of gets like less attention. So like it's one of the reasons why we are focusing on this task itself. Okay, so in for our task, so large vision language models, or what we call LVLMs or MLLMs or just vision language models, whatever we say, it's a very good opportunity to solve this task, the pedestrian navigation. So when you're saying like what are LVLMs? So this is basically the models people who have worked with like a Lava or Quinn. So it's like a generative model that gives you an understanding about the image itself. Like if you send an image and a question, then the model will give you an answer like okay, based on the image. So these large vision language models are like based on like they're in very easy sense. If we just basically these models are just like vision encoders with large language models. It's like the vision encoder takes the image itself and it is built on the large language models and works in the token space and just gives you the output the in tokens. So and they take these large vision language models take multimodal input, like they can process image and text questions. So in today's session, we have already seen a lot of like this kind of multimodal models. So hopefully everybody knows what kind of these models are. Like it takes multimodal input, and the output itself typically is in language form. So why it can be a good fit for pedestrian navigation? Because since these models are very strong, especially to describe and reason about this complex visual scenes, and they can take open-ended question and answer. Like it's not fixed on one simple question, or since it's an generative AI model, it can take flexible question and based on that, it can give you an answer. And the natural interaction between the model and the human gives it a very good fit for this kind of task. So then we talk about then why the current large vision language models kind of fall short for the pedestrian navigation. So the first thing is, so we kind of identify 3 points. So the first one is there's no geometric understanding. So it's okay, it has some kind of geometric understanding, so it might be overstating a bit, but it's like they don't understand the visual the visual geometrical understanding. Like, okay, it's not like sometimes it doesn't understand, it mistakes for some things like one object ahead of another object. So or like which object is kind of left or the right of another object. These kind of things, these large vision language models don't work that well, because these models, when they were trained, they're mainly focused on describing an image, like what's there, not mostly about the spatial relationship, about the objects. And typically, they don't have depth estimation or say like distances. Like, say, for example, if we say, okay, there is a car that in front of the pedestrian, how far the car is, like even the estimation, it cannot, without post training or stuff, these models fail miserably. Like they can't do this kind of estimation. And one of the more important was the hallucination stuff. So this is like a very active research topic, like hallucination for large vision language models. So since responses are not that grounded, like sometimes these models generate the description of objects that are not in the image. So this can be very dangerous for pedestrian navigation task, because let's say it says, okay, there's a car in front of you and there's not. That's an issue. Or also, let's say there's a car in front of you and it says, okay, there's no car. It's a very accessible road. That's also another very hard issue. So these are the three reasons. Like we kind of say, like these are the three why pedestrian navigation for LVLMs fall short for the pedestrian navigation. So then we come into our model or framework, whatever we want to say, which is the WalkGPT. So WalkGPT is basically what we're calling is a grounded large vision language model at first. So what is grounded large vision language model? So other than the conversation, like other than the answer to the question itself, the model can also ground some of the objects that's coming in the generation. So when I say ground, it means like let's say the generation says sidewalk ahead. So, and then the model can also provide a, let's say, segmentation map for the sidewalk. Or the grounding can be anything, like grounding can also be bounding box or some other way. But that's what grounded conversation is. Like the output itself is in two forms, the conversation and some grounding into the image. Okay, that being said, let's see how the WalkGPT, the model that we developed, works. So let's say the pedestrian gives an image and asks, like, can you describe the path in terms of accessibility for a pedestrian, including segmentation mask for accessibility and harmful features? Then the model will at first give a assessment of the path ahead, which is something that already the vision language models can do at a scale. Like, okay, the path ahead is largely walkable with a smooth paved path, etc., etc. Then the model will also provide information like, okay, in this image, what are the accessible features and what are the, let's say, non-accessible features or harmful features are. So let's say these accessible features will be like the features that will help a pedestrian move from here to there. And obviously harmful features will be like be something like obstacles. So whenever this model is generating all this in text, like accessible features of sidewalk, paved trail, harmful tree, vegetation, buildings, it will also generate the segmentation mask of these features as well. Hence, the grounded conversation generation, the connection between the text and the segmentation mask. So this way, the user knows, okay, the complete understanding of the path ahead, what kind of features to look for, what kind of features to avoid, and what are the shapes. Let's say, what are the shapes of the features? So then the last thing that remains is that since we're still doing everything in 2D image and stuff, so the last thing that remains is the distance to these features. So, and for each of the objects that have been mentioned and have been given a segmentation mask, it will be given a distance, like an estimated distance from the pedestrian. Like, okay, sidewalk might be this much far away, PFTL could be this much far away. So by this way, now the user has all the assessment of the path. Like, okay, this is maybe the obstacle that I need to avoid. Okay, how far it is, and exactly what are the shape of that object is. So the pedestrian knows how it can avoid, and like exactly when he or she needs to avoid. So that's basically the input, output, and the overall inference time of our model. So the technical contribution of the WalkGPT would be okay. Instead of explaining this, let me just go into the architecture so we can uh, go much into details like how the model, the framework is actually working. So this is kind of like all those stuff. So okay, let me go over one by one because with this big picture, it's gonna be hard to follow through. Okay, if you guys can see my pointer, so this is our input space. These are the output space, and inside everything, you can think of like a big box, which is the work GPT. Right. So the input, as we said in the last slide as well, the input is like a one question, and visual input means just an image. So the question input, like, can you describe the paths, etc., etc., and given an image. So this goes, let's say, if goes through a tokenizer, if the large language model takes the text tokens, which we do not touch. The visual input, it goes through a pixel encoder, which we use SAM's VIT model to give the encoder embeddings. So these embeddings are in like an embeddings in the visual space. Then they go through this module, which are calling the MSQP, or the multi-scale query projector. So basically, this is like an advanced projector that kind of like projects the encoder embeddings to the, which is was in the visual space of the pixel encoder to the large language model space. So the visual input, the image is converted to the image tokens, the text is converted into text tokens. Large language model takes everything, they did their own kind of appending and stuff, and then it generates the output tokens. And in the output tokens, when we extract the output tokens into language, like we map it into language. So this is how the overall thing looks like. So we have some structured tokens to make sure that what we want, everything, like the model learns to generate all these structured tokens and the text inside these structured tokens. The first structure token is the assessment tokens, the inside the assessment block. So the basic assessment that we just seen, like intersection appears, etc., etc. Then the model generates these features, the crosswalk, sidewalk. So after each of the features, it generates it wrapped around self these P tokens, and after that, immediately that has the seg tokens. So these P tokens are made sure that this model generates this, let's say the crosswalk, right? Whenever the crosswalk is generated, it is bounded by this P token. So, and after the seg, and it is immediately followed by the seg tokens, which is used to generate the segmentation mask. So why are the design is like this? So it makes sure that the segmentation mask is coming from the actual generator answer. So this makes sure this is connected through this token. So whenever the crosswalk is generated, it is forced to generate through these P tokens and seg tokens. So, and these seg tokens is directly used to generate the segmentation mask. So now they are connected in the generated answer and the segmentation mask. So a segmentation mask cannot appear if the feature is not in the text. Then after this, we have these distance tokens. So within these distance tokens, the model learns to estimate like a distance from the pedestrian's POV, like how far the distance are. So, and whenever these sec tokens are in the generation, then we extract the hidden space of this hidden states of these sec tokens. So see the extractor, and each of these sec tokens work as like segmentation prompt to like a SAM segment anything model. And it goes through this another projector kind of thing like CTP, and which is trained through this this region element loss. So for each of the seg tokens, for we have like each of the object, and it gives us a one segmentation mask. So basically, that's like the overall pipeline. Let me just give you one quick overview. uh, Image goes into this image encoder, then this MSQP projector gives us image token. This question in text form gives us text tokens, goes into the LLM. Then this LLM uses these image tokens, text tokens, gives us these output tokens, and which is output tokens gives us the generated answer. And in the generated answer, we have some seg tokens, which is for the segmentation, which we extract the hidden states and use as to for the segmentation mask. Then we have the whole output, like segmentation mask, and also the generated answer itself. So that is the overall framework. So I'm just going to go a bit detailed, not that detailed, but a bit detailer than this figure. So the overall framework, just I just explained like everything like here. And so since you guys remember, hope you remember that we have this two new thing, MSQP and CTP. So I'm going to explain what these do. So this MSQP multi-scale query projector. So typically this large vision language model just have a uh, just a simple MLP or linear projector to do convert the image embeddings to the image tokens that are in the language space. So by doing that, it we're losing a lot of information. So what we did very simply is that when we get the embeddings from, let's say, the pixel encoder itself, we do it in multiple scales. Like we use, let's say we zoom it in multiple scales so that we can get the different information in different scales. And we have some learnable queries with, let's say, a couple of some learnable queries. So we divide into four stages. And so the learnable queries are also divided into four different sections. So these learnable queries just interact like using cross attention with different scales. And at the end, they are like concatenated and sent to the language model. So by doing this, so now the model has like multiple level information, which is like a very important part on how to do this kind of like fine-grained understanding of for the pedestrian navigation. So that's basically the what the MSQP is. Then we had another project of CTP. Let me show you from the original framework, like the sec tokens go through CTP and the pixel decoder. So what it happened, like sec tokens, the hidden states of sec tokens are in like much bigger, much larger in dimension. Like it's since it's coming from the large language model itself. For Lava, it works with like 4096 dimension, but when it goes to the SAM model, it needs to be dropped down into 256 dimension. So a lot of information is getting lost there. So it's a kind of way that how do we do it? Like we use an we kind of make multiple copies through an MLP and make sure like if for hoping that each time for each of the copies it has more information. So we are saying okay, it's still getting lost, but every time the projection happens and through another MLP we kind of combine different kind of information through this k times banks, and which is then at the end reshape and concatenated and send as like mapped sec tokens to the SAM model itself. And and there's a region alignment loss. So like how to train this kind of like this CTP. What it does is that very high level let's say there's a seg token for the sidewalk. So it does the cross attention to the image region that the sidewalk is actually is from the original seg tokens, and they use those as like pseudo ground truth to do the region element, like to create the positive pairs and negative pairs. So yeah, that's very high level. So due to interest of time, I'm not going to go into much details. Um, okay. So that's the architecture itself, but since you can see the architecture, it generates this kind of generated answer, right? So we need a data set. Like it's still being trained is a cross entropy loss, like a very supervised fine tuning style. But we need a data set that has all this information, like this kind of tags and this kind of distance. But there was no data set in available that can be that has this kind of like VQA for each of the images. So then what we did was that we kind of constructed a data set that we're calling it PAVE. So the images are from like a Google research data set called Sample. So what we do is that we take these images and we create this kind of like a VQA question through like a GPT-5. Then, so the input image. The image is coming from real life pedestrian camera. It's coming from a data set called Google Research Sample dataset. And they have images and they have like a distance for each of the pixel. But if you remember, we don't need a pixel wise distance for our task. What we are looking for is that object level distance. So what we did, like we use that depth map to create the distance for like the minimum distance for each of the objects. So this is like an example, like let's say the LLM to create this data set, like we take the system prompt, the whatever the features are present and the distance of the feature, like the minimum distance of the feature. And we ask accessibility of the features, like these are the accessible features, these are the harmful features. And we have the query to generate this kind of question answer pair, like, okay, can you describe the path in terms of accessibility, etc., etc. Then it gives us like, based on all the information, it gives us this kind of data set. And we use this VQA data set to for our like the loss function to generate the question answer. So yeah, the training recipe is that there's like for the conversation generation, we still use like autoregressive with teacher forcing. Uh, and for the segmentation, we use like some dice cross entropy loss. And the depth is for the depth estimation. So since this is an object level distance, we don't do anything fancy like have another depth head or anything. So what we do like it's like the model learns to estimate depth when the distance for each of the object when in the like in the post training when it sees the data and it starts to learn to generate this distance of these objects through this cross entropy loss. So the theory is that the model has the inherent capability to calculate this kind of object level distances, but since in the pre-training it hasn't been done so if we just did this on the post-training, the model starts to learn this like object level distance. And since the model the generated answer is like coupled with these features and the seg tokens with the segmentation mask, this works quite well. Like the model knows, okay, whenever it generates, let's say, sidewalk, it knows, okay, exactly where the sidewalk is, because since they use this seg token to generate the segmentation mask, so it has much more understanding like where the sidewalk token is. So since the model knows where the sidewalk is, and whenever we do in the supervised fine tuning, we feed that, okay, sidewalk is like 5 meters away, then the model starts learning gradually. So that's like, again, like the high level idea of how the training is working. So yeah, for the interest of time, I'm gonna skip this experiment setup. So we have this quantitative result. So like we compare against all these grounded large vision language models. So same models that can also do this kind of like segmentation and conversation generation. So this is the big table. Uh, we so two main important thing to see here, like for the zero shot versions of these models, they fail to do the distance estimation, and they perform very poor on the data set that we curated. But after fine tuning in our data set, they kind of achieve a bit good good results, but still, based because of the newer techniques that we use, our model outperforms those grounded conversation. Okay, some qualitative results. Question, answer, segmentation mask, estimation. Then some there was some further analysis, like we also tried to see like how good the segmentation quality is, since our model is not just only segmentation, to see like how much it performs like compared to like popular sort of segmentation model like UNet or Sweden UNet. So it shows that it kind of is in the margin, but it's obviously not the best. We cannot beat a vision only segmentation model. And we also see that that model improves the hallucination, as since we are doing the grounded conversation, so it only generates the stuff that that's in the image because of the grounding. And ablation study, which I'm going to skip. And there's one interesting thing that since we check some of the limitation like failure cases, like what happens. So one of the thing is that whenever model fails, in some cases, like whenever the reflections are very hard, like let's say in this image, the building has like glass buildings, and the model gets confused because these glass buildings reflects very strongly of the path, and it says like, okay, this is not an accessible path, but which is actually is. So this is one of the issues. Like we found out, like this can be solved through like there could be multiple ways. Let's say we're using only single view 2D image. It can be solved through multi views, maybe some 3D images, or further it can be extended to videos, because right now we're just taking 2D single images. Yeah, that's pretty much it. Like we introduced grounded navigation and mask distance guidance, and we have this PAVE benchmark for everybody that wants to work on it, then can use it. So that's my presentation. Happy to take some question.